Yeah, first off, I'm really happy to be here, and I'm particularly happy to be here because about 10 years ago, I went to a machine learning summer school as well, and I have really great memories of it. So it's actually quite nice to actually be able to speak at one for the first time. So definitely fun for me as well. My name is Mark van der Wilk, and I'm at the Department of Computing at Imperial College London, where I'm essentially growing a research group with basically two main focuses. One is on Gaussian process inference and while doing accurate Bayesian inference in these kinds of models. And we're trying to use theory to make reliable autonomous decision-making systems. So we're trying to make these methods really work very well and use kind of theoretical guarantees to make sure that we don't need to choose any parameters in ad hoc settings. So that's one research direction. And the second research direction, which our group kind of focuses on, is the question of learning inductive bias in neural networks. And so basically the question is, how can we easily learn the architecture of neural networks? And this basically leads to what I think is an interesting long-term question, which is, can we find a rule that determines when neurons should be connected? Right? So backpropagation tells us what the rates of connection should be if we know the connections, but can we find a rule that actually tells us which neurons should actually be connected? So that's a long-term goal that we're working towards, but we've got some kind of shorter-term progress, which I would like to tell you about today. So to start off, I just want to motivate the problem that this line of research is looking into. And basically, that's the problem of hyperparameter selection and architecture design. And so this is something that you have to do every single time you train a neural network. And it's costly, it's cumbersome, right? So there are tons of decisions that you need to make when designing a neural network, like how many layers to use, how many units you want to keep in a layer, what the layer structure should be, right? So whether you want it to be convolutional, and there are actually a whole bunch of convolutional types of layers. So these are called group convolutions, and you might need to pick the right group. You need to pick whether you want skip connections, how much pooling to add, where to add the pooling, like what region to add the pooling over. And then you've got data augmentation parameters. All these things you need to select somehow. And I think that this problem is only going to get worse as architectures are going to get more complex. Right? So multitask architectures are something that is probably going to happen more. We're probably going to see more multitask architectures in the future. And there we need to ask the question of, well, which tasks are related enough for them to share layers? How many layers should they share? At what point should they branch off? You know, what kind of layers do we need to use in each of these task-specific parts? And also, how difficult is each task? So how much capacity should we add to each layer? So basically, I believe that the number of choices that we need to make is only going to increase as our architectures get more complex. Now, currently, the main tool for selecting these parameters is basically trial and error, right? So there's a nice word from statistics that's given to trial and error. So this is called cross-validation, but it's basically just try it and see how well it works. Now, the goal of this line of research is basically to make selecting parameters for all these questions is to make it as easy as learning the weights. That's the goal. So why do we care about architecture? Well, it's because an architecture of a neural network determines the inductive bias of a neural network. Now, every prediction problem needs an inductive bias, right? So in this kind of toy supervised learning task, we're aiming to find a particular function that maps from an image to a label. And we're basically given a bunch of training points. And the goal is that we actually find a function that predicts well on an unseen image. Right? So the inductive bias is the rule that determines what your prediction is going to be for an unseen input, given that you've seen all the other training data. Now, there are many ways that architecture determines inductive bias, but today we're going to focus mostly on invariance and equivariance. And these inductive biases are well, incredibly common, and they're included in architectures through, for example, convolutions. And the normal convolutional layer is one example of this, where you apply the same filter to different regions of the image, right? So this creates a kind of a translation equivariance, or a translation invariance. So it means that you can learn how to predict for a feature in a different part of the image if you see it in your training set in other parts of the image. But there are other types of convolutions as well, for example, that generalize this picture to rotations. So that allows you to generalize across rotations better. Now, yeah, so the examples of our research that I'm going to show today try to answer the question of how we automatically adjust invariance properties in layers, right? So this is an example of automatically adjusting an inductive bias in a neural network. Now, by the way, I'm also happy to take questions throughout the talk. So if you do have any questions at any point, then please raise your hand and I'm happy to pause and discuss a bit. So to summarize, I just want to give a bit of a summary of the overall approach that we're going to look at today. So our goal is for a given data set, we want to find or adapt the inductive bias to work well on that data set. And in order to achieve that goal, we're going to find a method that has two requirements. So firstly, we need to find a parameterization of different inductive biases, right? So every machine learning method needs to parameterize its class of solutions. So we need to do that for inductive biases. And secondly, we need to find a learning objective, right? So we need to find a value that if we maximize it, it'll give us an inductive bias that actually works well. And in particular, in line with what I was saying earlier, we want to find a learning objective that's easily optimizable through backprop, right? It's much more convenient than this trial and error cross-validation procedure. So what we'll specifically look at are invariances and equivariances that are parameterized through transformations on the input. So this is really similar to data augmentation, right? That also introduces a particular inductive bias to a machine learning method. And we're also going to look at invariances and equivariance where the transformations are applied on the filter, right? So that's the kind of convolutional layer parameterization of an inductive bias, right? So those are the two ways that we're going to parameterize our inductive biases. So that's number one. And number two, to find an objective function that allows us to learn the right inductive bias, we're going to see how Bayesian inference can help us with finding a learning objective. Now, at this point, I also just want to mention that this is actually the key thing that I think is interesting about Bayesian inference, right? So most people know about Bayesian inference as a way to get uncertainty out of their predictions. But actually, I think uncertainty is cool as well. But what I really think is kind of amazing is that Bayesian inference can answer the question of which inductive bias you should use. Yeah, and in particular, I'm going to talk about single layer and deep models. Now, a lot of my research focuses on single layer models, and in particular, Gaussian process models. And I'm interested in this because it kind of allows you to study the key properties in a model where you can actually solve all the equations in a mathematically very precise way. So I think single layer models are often a very good illustration of the key properties that we're researching. But I also want to talk a bit about some research that I've done together with some collaborators on applying these ideas in deep models as well, because the ultimate goal is to do this well for deep neural networks and, yeah, try and make things easier for deep learning practitioners. Okay, so to start with, I want to talk about invariance, data augmentation, and the training loss. And basically what I want to talk about is why we need something a bit more complicated than our usual training error in order to find the right inductive bias. So, right, so let's start with data augmentation. So data augmentation is a procedure by which we can add an inductive bias to basically any machine learning model, any supervised learning model. So imagine that we have a particular classification task or something, and we know a priori that we should give the same classification to multiple variations of a particular input image. So in this particular example, we've got an image of a cat, and we know that a cat is still a cat, even if we rotate the image slightly, if we mirror it, or if we kind of zoom in, it's still a cat. So this is an inductive bias, right? We know that we have an image in the training set, but we want to generalize to all of these images with particular transformations on them. So how does data augmentation incorporate this inductive bias into a machine learning model? Well, it does so by essentially creating a larger data set with just the transformations applied on the training set. And then we just train our predictor on the larger data set. So to put that in a different way, so imagine that we know that our regression function, our classifier, has the property that its output stays roughly the same. That should be an approximately equal sign as a transformed input. So for example, to small translations, rotations, scale changes, etc. Then our procedure is essentially we apply random transformations to the data using a particular probability distribution over transformations. And then we simply minimize a new average training loss on a new larger data set. So that allows us to find our weights of a particular function, possibly a neural network. Right, now what happens if we don't actually know what transformations we want to be invariant to? Right, so that's when it becomes a learning problem. Right, and we can follow the usual machine learning procedure of essentially first parameterizing our unknowns. So in this particular case, we would add some parameters to this distribution of our transformations. And then we could try learning the unknown parameters theta. Right? So that's one way in which we could try and learn the inductive bias that we're trying to incorporate into our model. And to make this concrete, I would say that we could think about these parameters theta as learning which and the amount of the transformations to apply. So for example, if our data augmentations can contain rotations or scales or translations, then this parameter theta could contain how much of each one of these transformations to apply to our data set. And in this running example, we might, so this is roughly MNIST, right? So we might want small rotation invariance, but large translation invariance. Right, so there's small rotation invariances because we don't want to confuse 6s and 9s, but we still want to roughly give the same output if they're kind of like small variations. But we want a different invariance for different tasks, right? So imagine that we're trying to classify images on envelopes that are randomly rotated in front of our camera. Then we would want to be completely rotation invariant, right? So this is why we might want to learn a different inductive bias for different data sets. All right, anyway, so we could follow our normal machine learning procedure, and then we could say, well, how do we find the right parameters theta? Well, could we not just minimize minimize it with respect to both the weights and the parameters of the augmentation? And one reason why we could imagine that this would work is because it does successfully learn the weights, right? It doesn't do anything too bad there. Now, sadly, this doesn't work for hyperparameters, right? So for parameters that control the inductive bias. And the reason for this is that all inductive biases, and including invariances and therefore data augmentation, they're essentially a constraint on our model F, right? So on the function that maps from our input to our output. So, right, think about this. An invariance is a constraint that says for all these transformed inputs, we want to have the same output. Right? So that's a much more constrained model class than just like a fully connected, unconstrained neural network. Right? So because an invariance or an inductive bias is actually a constraint, that means that adding this constraint to our model won't improve the fit to the training data, right? It might leave it unchanged, but it won't improve it. Right? So at least the easiest way to minimize the loss in this case is to make the augmented image, the transformed image, the same as the input image, right? So essentially to add no augmentation at all. But we know that this is not the solution that's going to generalize best. So here I've got an example of this rotated MNIST data set that I kind of also mentioned earlier. So here you're trying to recognize handwritten digits, but randomly rotated. So imagine someone throws a bunch of envelopes on your desk from a big bucket. The augmentation distribution that we might want to learn is to randomly rotate these digits to augment the data set with theta controlling by how much. And then basically here, in the red, I show what happens when you optimize one of these point estimates. Right? And we basically see that even though we initialize it at like something slightly higher than 0, it immediately goes down and learns a data augmentation of 0 degrees. So it doesn't do what you want. Now, funnily enough, there's another method which we will talk about today, which actually does recover the right invariance. Okay, so this is basically the reason why we use trial and error or cross-validation, right? So that we can actually test how well a particular inductive bias generalizes on a validation set, and then we choose the invariance parameter that generalizes well. Okay, so if we can't use the normal training loss, well, what objective function do we use then to find the inductive bias? Well, it turns out that this is a very well-studied problem in Bayesian inference. And there's a solution to it called Bayesian model selection. So as an analogy, I first want to start with a different inductive bias to invariance, but it illustrates the same principle. So essentially, imagine that we've got a one-layer neural network, which is basically a basis function model with these little Gaussian nonlinearities. Then if we want to learn a particular function, we basically need to learn these weights. And the hyperparameter, which controls the inductive bias, is the width of these basis functions, right? So if we make the width of these basis functions shorter, the inductive bias will be that it's more wiggly. Whereas if we make these basis functions larger, the inductive bias will be that it's kind of a more smooth function. Now, we want to essentially find both the weights and these hyperparameters, which control the wiggliness. So what we normally do in these situations is that we minimize the training loss with respect to W while keeping the hyperparameters fixed, and then we might do this cross-validation of the hyperparameters. But we would like to find a gradient descent procedure for theta. Now, to really kind of convince you that the normal training loss isn't the right thing to do here, I'll show you a short video of what happens when you optimize the width of these basis functions with respect to the training loss only. So we see that basically we get a perfect fit on the training set, exactly what we asked for, but hopefully you would agree that that a 0 prediction isn't a particularly good prediction for the test set. So why does this happen? An inductive bias is a restriction, right? Like making the function smooth is a restriction on the type of functions that we can learn, and that won't help the training loss. So what we do is cross-validation. And our goal is to find a different optimization for these hyperparameters theta. Now, I just briefly want to give an overview of where the Bayesian model selection criterion comes from, but if you're not familiar with this, then just keep the high level in mind. But Bayesian inference basically tells us a procedure to find any unknown in a statistical model, and essentially it just tells us put a prior on one of your unknowns and then find the posterior. So we can do that for both our function and our hyperparameters. So if we do this, then basically we get our usual posterior, which is roughly similar to what you get if you minimize the training loss for fixed hyperparameters. But it also tells us how to get the posterior of the hyperparameters. So what's nice is that your normal posterior over your weights over your function is kind of unchanged, but your posterior over the hyperparameters now uses a different likelihood to your normal posterior. And this likelihood is a quantity called the marginal likelihood, which you get by essentially integrating your likelihood over your prior on functions. Now, the way that Bayesian model selection is commonly done in practice is that we just maximize this marginal likelihood with respect to our hyperparameters and then predict using the posterior. But the key thing to notice here is that Bayesian inference is telling us to maximize a different objective function to the normal training loss, which we usually minimize. And the really cool thing about this method is that if you can at least compute this marginal likelihood, then you can use gradient-based optimization for it, which is super convenient. So to give an illustration for what happens on this toy example, if you use the marginal likelihood instead of using the training loss, this is basically what happens. So we start at this overfitting solution, and then it recovers and goes to a solution that fits the training set a little bit worse, but probably looks like it's going to generalize better. Yeah, and the nice thing is it can be computed on the training data only, and we can compute gradients. So no more trial and error. Hyperparameter selection is just as easy as learning the weights. And we want to learn neural network architecture parameters in this way. Yeah, so notice how I haven't explained why this works. I've hopefully only given you an illustration that it works, but I've got a few illustrations later that I can show after the talk if you want to see why it works. Okay, so how do we use this to then learn data augmentation? So in order to learn data augmentation using this Bayesian method, we first need to formulate a kind of correct Bayesian way of incorporating data augmentation into a model, right? So simply making the data set larger isn't really correct from the Bayesian point of view, because basically the only flexibility that you have when specifying a Bayesian model is the prior and the likelihood. So back in 2018, I had a paper that did this in Gaussian processes, where we kind of came up with a Bayesian interpretation of data augmentation. And the key idea in that paper was to see data augmentation as an invariance that you incorporate in the function that you're trying to learn, rather than a change to the data set. And basically, to cut a long story short, it's a different parameterization of the function that you're trying to learn. So in the model that we looked at, we essentially said that the function that we were going to parameterize was essentially our normal basis function model, but averaged over the augmentation distribution. Now, if you average a function over a particular set of perturbations, you're essentially smoothing it over those perturbations, which makes it more invariant. And there are some theoretical arguments that connect this to kind of strict invariance as well. So this is basically the parameterization that you can use to do this. And once you've chosen this parameterization of the function, you can then define a prior over the weights and the likelihoods, and then you basically defined a Bayesian model with unknowns that are the weights and unknowns that are these hyperparameters which control this transformation distribution PT. So given this view on data augmentation, this now gives a well-defined marginal likelihood which we can optimize, at least in principle. The problem is that we can't actually compute it, because doing this this integration over the data augmentation distribution, that is usually intractable. So that's a typical problem that we encounter with Bayesian inference, is that we encounter intractable integrals. So how do we deal with this? Again, I'm just going through this very quickly, but I just want to give you the key ideas of how we deal with this. So we basically use a very common method to deal with intractabilities in Bayesian inference. We use variational inference. And what we were interested in is a tractable approximation to the marginal likelihood, right? So that we could optimize the approximation to the marginal likelihood with respect to our hyperparameters instead of the exact thing which we can't compute. And yeah, what's great is that variational inference essentially gives us a way to find both an intractable posterior and the marginal likelihood at the same time. So it gives us exactly what we need. So following the usual arguments, we get a variational lower bound. And then the trick is to notice that the intractability that makes this problem special is actually in computing the function that we predict with, right? So that's where this integration over the data augmentation transformations comes in. And to deal with that, we essentially notice that if we have a log concave likelihood function, then we can apply Jensen's inequality to it. So we apply a multi-sample Jensen's inequality to make that band as tight as possible. And the procedure that we end up with is basically that we just need to do a few forward passes through our predictor using our transformed inputs. And then we take the average of that, just like how we define the invariant function, and then we feed that into the likelihood instead. And that then gives us a lower bound to the true marginal likelihood. And so this kind of multi-sample band was investigated in a bunch of our papers in the last years, where we looked at it, where we looked at the implications of having this Bayesian correct way of incorporating data augmentation. But for now, I'll just focus on the papers where we use this to learn the data augmentation. So just to give a brief idea of the results that we get here. For this rotated MNIST data set, if we then now optimize the variational lower bound with respect to both the posterior over the weights and the hyperparameters, we now avoid this collapse of the invariance, and we get an invariance that gives us a fully rotationally invariant model, just as we would expect for this data set. So it solves the problem that we had earlier. And the nice thing is that we can just use gradient-based optimization for this. So we don't need trial and error, and we don't need cross-validation. So yeah, to give maybe a slightly different result. So here we applied it to the rotated MNIST data set, and we observed that we learned a fully rotational invariance. But what's interesting is that we can apply exactly the same model to a different data set, which needs a different inductive bias. So in this particular case, normal MNIST, and then it learns a different inductive bias, right? So for normal MNIST, where you don't want to be fully rotationally invariant, we learned to get only small perturbations, so small translations, small scales, small rotations of the input digits. And these are basically the types of transformations that people have found by manually tuning data augmentations as well. But we could learn these parameters through backpropagation. So the cool thing of this capability is that you can now throw one model, one architecture onto two different problems that would usually need to have had different inductive biases encoded into them. And this method can find them automatically. And it actually helps performance as well. So maybe now is a good point to pause for a few questions. Yes, thanks. The previous graph, yeah, this one.
After certain number of iterations, the model will provably rotationally invariant.
Well, provably is a difficult word, but so I wouldn't say that in general, but in this particular case, because it learns to rotate the images completely through one full circle, then that does end up making this model almost exactly rotationally invariant, which you would expect for this data set.
Variants, like how they define physics, are really about preserving certain constants.
Yeah.
Here, an inductive bias is like an approximate invariant.
Yes, well, that's exactly what we've done. We've parameterized a whole class of degrees of invariance, right? And the exact invariances are kind of extreme points on this parameterization. Yeah.
Is there any situation where I wouldn't want exact invariance, but would like that approximate?
Yeah, so is there any situation where you don't want exact invariance? Well, MNIST is a great example for that, right? Because you want to be a little bit rotational invariance, but not rotationally invariant, but not completely.
Through these data augmentations.
And in this case, it's parameterized through these data augmentations. Yeah, that's right. Another question?
If you eliminate some of the numbers, so say I have number 1 and number 8 left, which already rotationally same, would it then go to 90 degrees, do you think?
That's a good question. Yeah, so we did a few experiments like this, and yeah, the degree of invariance that you learn is does depend on it definitely depends on the data set. Yeah. Now for the non-rotated MNIST, basically most of the benefit that you get is already in small rotations. So the generalization the generalization improvement that you get from becoming fully rotationally invariant isn't very much there, and so the model doesn't really pick up on it very much. But that's basically just because there's no hint in the data set to say that there's a reason to think that it would actually help more. But I mean, again, in the rotated MNIST example, it really picked up on the rotational invariance there and said, you really have to be completely rotationally invariant.
Imagine there was a local minimum, right? For some of the symbols, you don't need to rotate them.
Yeah. Yeah. So local minima is that is a well, with simple parameterizations of invariances, local minima might be a problem. Now, basically, one reason why I'm excited about this line of research is because what I think we should be doing is parameterizing more flexibly different types of invariances. And just like with highly parameterized neural networks, maybe the issue of local minima might become less bad. But I mean, there is this question of well, if you make the parameterization larger, then maybe you might start to overfit again, right? So basically, this is an open research question to how much you can push this and how to do that.
So for the previous part, just to check, if your initialization, which is the prior indicate, right? If that had been at a multiple of 180 degrees, the variational inference model would have stayed there, right? If I had said I can rotate up to 720 degrees in a way, sort of that just gives me the same distance all over, and that sort of would have been what you would have ended up with. Is that correct?
So basically, you're saying that rotating through one circle is the same as rotating through two circles. Yeah, so those are indistinguishable. And what's cool is that the marginal likelihood only cares about the effect of parameters in the sense, in the way that they influence the predictions, right? So the marginal likelihood for those models is exactly the same.
And so you sort of talked about it's normal effective interval, and you found it. Is it depending on any sort of you can only use 1 or 2 layer networks or?
Well, so far I've only described 1 layer networks, right? So the reason for that is that variational inference gives you very accurate marginal likelihood estimates in these shallow cases. Doing that for deeper models is an open research problem, but I've got something to show about that in a few slides' time as well. So yeah, we absolutely are trying to make this deeper, and there was some initial hints that it's actually pretty possible.
And so you talk for more complex augmentations, as you mentioned earlier, we can sort of more easily control the amount of augmentation to apply, how often we apply, rather than sort of just not all augmentations are differentiable, right? And do these need to be differentiable or smooth? Or
yeah, do these augmentations need to be differentiable? So if you want to learn them through backpropagation, then yes, they do need to be differentiable. But I mean, the marginal likelihood as a principle still applies even if you need to make a discrete choice. Or well, I mean, it's a little bit more. Some people debate that a little bit more, but I think that there are plenty of cases where that is the case. But then the question is, well, how do you? One of the benefits of this approach is that you get the power of gradients to search over your augmentations, right? And if you've got discrete choices, then that advantage over cross-validation disappears a little bit. Now, I would say that arguably the success of deep learning comes from the fact that it uses gradients. And lots of very successful papers in deep learning essentially aim to make a non-differentiable problem differentiable. So I would kind of say that it's an interesting research problem if you have an inductive bias, which might be a discrete choice. How do you make that differentiable so that you can easily search over it? Another question?
What do you think about that problem?
Yeah, so auto-augment, these are also other automatic augmentation discovery algorithms. And basically, I mean, the good thing about them is that they already work on the largest scale models. Right now, the bad thing about them is that they're basically, well, they're a clever way of brute forcing this, this cross-validation procedure. Right? So often they require an outer loop and you know, it requires training loads of networks at an inner loop, you know, so yeah, it's good in the sense that you can throw tons of compute at it and then solve the problem. But the cool thing here is that you can adjust your data augmentation as you're training the model, right? So, I mean, I don't know if this is really possible, but I mean, what I want to do is make sure that you can actually adjust these things in one training step for one neural network. That's that would be the dream, and that would be a lot more computationally efficient, right, than training loads of these neural networks in an inner loop. I'll have time for some more questions later, but thanks very much for the questions. That does make it a lot more fun. Okay, so I've only got one slide on this, but the two first authors are actually here in the audience today as well. We recently have also kind of tried to apply this principle to deep neural networks. And I'm really quite excited about this because it shows that at least this principle might be able to actually contribute to deep learning practice. It's still early days, but the fact that we can go from shallow to deep, I'm quite excited about it. So basically, the principle is really simple, right? The principle behind this idea is that we just want to compute or approximate this marginal likelihood, and then we can find gradients with respect to it to optimize invariance parameters. And so yeah, together with Alex Immer and my students at Imperial, Tija van der Oudere, we used essentially a Laplace approximation with a Kronecker factorization. I won't go into the details, but it's a type of an approximation to the marginal likelihood of a deep neural network. And then we backpropagated through that and found that similarly as in the shallow case, we could actually learn augmentations that improve performance all the way from small data sets to large data sets. And what's cool is that this Laplace approximation can be justified as a Bayesian approximation, but it's also related to this intuition that deep learners have had for a long period of time, which is that flat minima generalize well. And the Laplace approximation, when you try to optimize it, essentially biases your neural network to find architectures or invariances that make the minima in terms of the parameters really flat. Now, one interesting discussion that I've had with some colleagues is they've asked me like, oh, well, you know, deep learners have known for ages that flat minima are good minima that generalize well. What's new about your paper? And why does the Bayesian interpretation actually contribute something here? Yeah, so the answer to that I usually give is that what I think is interesting is that deep learners have known for ages that flat minima generalize well, but they haven't used it to actually do architecture search. Right? And the idea that you could use that for architecture search, that comes from this Bayesian route through the Laplace approximation. So whether or not the K-factor Laplace approximation is actually a good approximation to marginal likelihood, I think this Bayesian way of thinking, and particularly going beyond the uncertainty quantification way of thinking, I think that can actually lead to methods that can contribute to deep learning. So yeah, I'm very excited about this line of research at the moment. All right, so finally, I also just want to show another direction that we're looking into, and that's in kind of more in learning equivariance more as a property of the weight architecture rather than as a data augmentation. Right, so in a certain sense, data augmentation is quite a brute force method by itself, right? Even if we can actually find the parameters of it through gradients in an easier way. it's still a little bit unsatisfying maybe that in order to make an architecture invariant, we just have to pass loads of transformed images through the entire network. Right? And the cool thing about convolutional layers, for example, is that the invariance properties are baked into the weight structure. So what we tried to do in this work is to see whether we could use the same principle of using the marginal likelihood to learn weight sharing structure like convolutions do, in the weight structure. So so previously we saw that we added invariance by essentially transforming the input image. And what we want to do is we want to learn equivariance by transforming the weights, just like group convolutions do, right? So if we think back to the image of translational convolutions, the way that they add invariance properties is by taking the same filters and then transforming them by translating them all over the image. Now, different types of invariances can be incorporated in these convolutional structures by transforming your weights in a different way, right? So instead of taking a translation, one can also take, for example, a rotation to create rotational invariance properties. And what we want to do is we want to flexibly parameterize a neural network layer that can automatically learn how to transform the weights to get different invariance or equivariance properties. Now, how does this relate to the data augmentation, so the input transformation way of viewing things? And it turns out that, again, for a single layer, transforming the input is basically equivalent to transforming the weights. So that's nice because that means that all the tools that we've seen so far can be used to learn weight structures as well as input transformation structures. So just to give you, again, a kind of light overview of how this works, our construction for an invariant function using data augmentation was taking this expectation here. And if we use a neural network to parameterize our function, that means that our feature representation is a nonlinearity applied to weights applied to a transformation of the input image. And what's interesting is that we can choose whether we want to apply that transformation either in the right-handed direction on the image, or we can exactly equivalently, choose to apply this transformation onto the weights by applying it to the left-hand side first. So basically, this insight allows us to instead transform the filters to learn actual convolutional structure in a layer. So this will be presented at UAI in August. And again, I've got some kind of images. So let's see what happens on the rotated MNIST data set. So what I've plotted here is essentially the weights of our neural network. And currently, it's initialized to be a network that behaves like a fully connected neural network. And as we learn, what we'll see is that these filters arrange themselves into rotated versions of each other. And particularly if you take a look at this filter to the left here, you'll see that as it trains, it learns to rotate, right? And that's essentially the layer becoming a rotationally equivariant convolutional layer. So see that as we learn the filters, it also learns to arrange the filters in this filter bank way, but maybe in a slightly different filter bank to how you're usually used to seeing them. So instead of having these translation transformations, we have rotation transformations. And this makes the network rotationally equivariant to deal with this rotated MNIST data set. So if you particularly take a look at this one to the left here, you actually see that it learns to rotate. Now, the power of this method, again, comes from when you apply the same architecture to data sets that require different inductive biases, right? It's the adaptation of the inductive bias that makes this powerful. So here we had this rotated MNIST data set. But if we applied the same model to variants of MNIST which have the digits transformed in different ways, for example, translated or scaled, translated or scaled, for example, then we get filters that arrange themselves according to different transformations. Right? So on regular MNIST, you kind of get filters that are only locally perturbed in accordance with the results that I showed earlier. And for a scaled version of MNIST, you see that these filters become scaled versions of each other. So this allows it to generalize across scale. And similarly, for a translated MNIST, you see that the filter basically stays the same, but gets scaled, translated across the input space. So that's really what we're looking for here. We're looking for a single architecture that can adapt to different inductive biases that are needed for the setting that we're looking at. So yeah, basically to conclude, there are 4 papers that I spoke about in this talk. So there's the paper on learning invariances using the marginal likelihood. This basically did this incorporation of data augmentation as an invariance and learned it with the marginal likelihood, but used it, but did it in single layer Gaussian processes only. We looked at this in deep neural networks, where we incorporated data augmentation in this Bayesian correct way into deep neural networks. So that was another paper with Seth Nabarro, who's also here today. But we didn't do any learning in these deep networks. And then with Tigo van der Oudera, we worked on doing the weight version of this representation of invariance and equivariance, but again in shallow models. And then recently we kind of put it all together and did this learning of invariances in deep neural networks using these Laplace approximations. Right, so to summarize again, our goal was to find an inductive bias that was right for a particular data set. We saw how to parameterize different inductive biases, and we saw how to find a learning objective for these inductive biases. And particularly, we saw that it was optimizable through backprop, which made it easy. And specifically, we looked at parameterizing invariances and equivariances by transforming the input, so that was data augmentation, and transformations on the filter, so that gave us convolutional structure. And we saw how Bayes can help with finding a learning objective. And we looked at single layer and deep models. So, right, so what's next about this? Well, essentially what we want is something better than trial and error to design neural networks. And yeah, at least for these invariances, Bayesian methods are making finding these as easy as backpropagation. So essentially, I think that this can make neural networks more accurate, right, by finding better inductive biases, easier to use by taking the kind of human engineering out of the process of coming up with a good neural network, and more energy efficient, because I essentially believe that neural networks with the right inductive bias can be smaller, which can reduce the cost of actually training them. Now, basically, all of this is a step towards maybe a bit more of a longer-term goal, which is to get neurons that can decide how to connect to other neurons, as well as to find the weights between them, right? And this invariance example is almost an example of this, right? So convolutional structure is a type of connectivity structure, and we kind of saw a continuous way in which we could learn this connectivity structure. Now, the next steps are essentially to actually do this on the neuronal level to make this a lot more efficient and to make the training really efficient. Now, how should we do this? Well, the Bayesian approach is one particular way, but there are many alternative approaches which could also work. So meta-learning, I think, is an approach that people have also taken to kind of find these invariances in neural networks. And so I'm particularly excited about the Bayesian direction as well. Causality can also come into play when trying to find good network architectures. And there might also be wackier ideas that we haven't really even thought of to allow us to grow better neural networks. So which one is going to be the right way to go? Well, I don't really know, but that's why we do research. But what's interesting is that I think these results using the Bayesian view and things at least show that something more is possible. I'm also hiring PhD students every year. So if you're interested in maybe working on some of these things, then do get in touch. So yeah, with that, thanks very much for your attention, and I'm happy to take any more questions.
What kind of data set does basically assume that the distribution of your data set doesn't change? What about when it changes?
Yeah, so what about when you've got data set shift, right? When the distribution of your data set changes? Yeah, so I think that this is a super interesting question, right? So basically what you're asking is, how do you do out of data generalization? Well, I do believe that these kind of approaches can help with this and can do something more than the straightforward deep learning approach. Right? So finding an invariance is essentially sort of like finding an underlying rule that holds more generally than just what you see in your individual data points. So I am really excited about using these tools as a direction to kind of tackle this problem. I think it's an interesting, but we haven't shown it yet. Yeah, definitely an interesting problem, and I'm hopeful about it. Any other questions? There are some questions I didn't get to earlier. Okay. Another question over there? Yes. Yeah, so different applications of the filter, right? So in translational equivariant models, you have the same filter which are applied to different image locations, right? So in the rotational example, we had the same filter which was applied to different rotations of the filter, right? And in the scale example, this is actually the best one to kind of see it in. You see the same filter that applied to different scales of the image. Yeah, and well, so the translational version, it didn't work that well, but you can see, well, actually, it does actually learn that it translates the entire filter. It doesn't get the locality yet, right? So there's one big difference between the filters that we get on translated MNIST here and a normal convolutional method, is that a normal convolutional method has much more local filters. And there are good reasons to believe that this is a desirable solution, and we are working on new parameterizations that might make it easier to learn these kind of solutions as well. Does that answer your question? They're different versions of the same filter. Right? So similarly to in a normal convolutional layer, you've got the same filter, which is applied to different locations in the image, right? So you've got the same filter, but translated, right? So you can think about that filter as being applied in the original image domain, but then it's just a little filter in a different location. So here, that's what we're plotting here, right? The different versions of the filter, but in the image domain. Now, the reason why they're the same size as the image is because we start off as a fully connected layer, right? So we can interpolate from a fully connected layer to a convolutional structure. And yeah, so this locality property of the filters is something that we don't quite get yet. I can come if yeah, another question.
Varying networks, and then these are those provably equivariant networks. Then these networks are big intermediate features, which are not just scalars anymore, but these are, for example, vectors which can go to.
Yeah.
Kind of guarantee that they're equivariant.
Yeah. So here we don't have the guarantee that they're equivariant. Again, similar to your question earlier, strict equivariance is one of the extreme points on this parameterization. But it sort of allows you to be approximately equivariant. And I would kind of argue that this is a feature. It could allow you to be exactly equivariant if the data kind of tells you to, But there's, and this is actually an interesting question that we're also still working on like how to parameterize these interpolations of equivariances and stack these layers on top of each other. So yeah, this is something we're actually working on. Happy to chat more.
Do you have to tell it beforehand or which of these invariances you want to learn, or is it one set of transformations?
Yes. So basically, every machine learning method needs to parameterize a set of solutions from which it picks a solution. Now, the strength of machine learning method, in part, comes from how little you need to parameterize or how general your parameterization is. In all the examples that I've shown so far, we've parameterized affine transformations or local deformations, and that's what we've seen here. But like I was saying earlier, it would be to make this method stronger, we would actually want to parameterize in a more general space. Does that answer your question?
In this case, when you were able to account for variances with the debate structure of the numbers, were you able to observe any change in the representation? Maybe it was more compact, or maybe tended to be disentangled, or was there like a change of this objective that we were able to
a change of the, sorry, yeah, I think I understand what you mean. Can you just say it again?
So the representation in the case when you include these inductive biases in the network.
Yeah, or we allow the network to choose which inductive bias to use. Yes.
Yeah. So was the representation different to, for example, one law?
Yeah. Well, I mean, so this does sort of show that there is definitely a different representation, right? So instead of just representing like different filter banks in a fully connected network, this network chose to behave more like a convolutional neural network. So that's definitely a different representation. You mentioned disentanglement. I think that this is another very interesting question that we're going to look at in the future. Yeah. Another question?
This is all related to the white learning. Like a lot of the invariances people are trying to improve the data augmentation in terms of white learning. How do you figure out method and then like how do you see the speed evolve in terms of like translating to research of white
Yeah. So how does this relate to unsupervised and self-supervised learning? Yeah, so I think that there is a bit more conceptual thinking that needs to be done to do that in the right way. But I mean, I do think that all machine learning, basically all machine learning right now is function approximation, right? And so if you can do something in a supervised way, then that provides you a very good foothold to do something in an unsupervised way, right? And if anything, this self-supervised learning trend is trying to make unsupervised learning look more and more like a supervised learning objective. So yeah, I definitely think that there's stuff that can be done there.
So the product here is very invariances, and by encoding them in the form of objects, and then making the network plane of like models of invariances.
Yeah.
Quite a natural.
Yeah, I definitely agree. I mean, so I'm definitely excited about the direction that this research is going in, and I'm excited about our results, but they are still fairly initial, right? Like it's not like a Swiss Army knife that you can then just apply in every application. So in this first example where we managed to do it in deep networks, we're still working on ResNets on CFAR 10. But you know, the direction is going in the right direction. Well, if there are no more questions, then I think we're exactly on time. So yeah, thanks very much for your attention.